Hello and welcome back to the channel. Today we're going to see how we can build an ARINC-429 transmitter using these three components. We have an Arduino. In this case I'm going to use an Arduino Nano. Then IC. This one is 74HC00. This one. And actually the real ARINC driver, which is this Holt. I'm gonna use this sorry, I don't know if you can see it, but by the way, 8586. It's an Holt 8586. So we're going to see how we can connect these three components in order to make an ARINC-429 signal generator, which can be controlled by the Arduino and is capable of doing both a low speed and high speed ARINC signal. It's going to be relatively cheap compared to the commercial solutions that are available on the internet. I also have seen some other videos of other people using Arduino in order to do the same thing. However, I mean they use parts which are difficult to source, and many times they are not produced anymore, or they are super expensive. In this case, the most expensive one is actually this one, the Holt driver, but it can be easily sourced from DGK, and is not that expensive. It's around 22 euros. So in order to understand how it works, let's move to the iPad to explain how it works. I forgot to mention that we also need dual rail power supply. In this case, you can use dual rail power supply from AliExpress, like this one. You get 12 volts and you plus 12 volts, and then on output you get the minus 12 volt, the ground, and the plus 12 volts. In my case, I'm gonna just use my bench power supply, which is the same, and for me it's a little bit more convenient. So the main idea comes from a video that has been published some years ago from the Labo de Michel YouTube channel. If you don't know, I really suggest you to go and check on his videos. Michel is a very clever guy, so I really suggest you to go and check on the hundreds of his videos about electronics and avionics, and in particular this idea comes from his videos 161. In that video, Michel basically explains how to build a similar ARINC-429 transmitter using also this part, this Holt 8586. But in his case, instead of using an Arduino, he used PIC microcontrollers. I don't know. I prefer to use Arduino, in particular AVRC. I'm more familiar with the AVRC. So, and the Arduinos are also easier to find. So that's why I prefer to use an Arduino. So that's the schematic. Basically, we have the Arduino supplied with 5 volts. And the Arduino communicates with a logic IC, the 74HC00. This IC is supplied with 5 volts too, and the Arduino basically communicates with the 74HC00 via SPI. So we're going to have a data and a clock signal. After that, the 74HC00 is connected in a clever way, which I borrowed once again from the Labo de Michel video 161 to give the right signals to the Holt 8586, and which then is going to generate the ARINC A and B signals. As I told you before, the Holt needs plus 12 volts and minus 12 volts to operate. So I'm not going into the details of the schematic, but basically the 74HC00 translate the SPI bus data into something that the Holt 8586 is able to understand. And basically the Holt expects 0 and 1 or 1 and 0 in order to give the ARINC signals. Okay, but there is a small problem. Actually, you see here that we have the clock, so we need to generate basically the right clock at the right ARINC speed, and you know that the low speed ARINC is 12.5 kilobits per second, and the high speed is 100 kilobits per second. Actually, as you know very well, I believe, the Arduino and the Arduino Nano, they all run usually at 16 megahertz. And when I started using this, the SPI driver, the standard SPI driver from the Arduino, I realized that I was able to to generate a clock suitable to have 100 kilobits per second, but I wasn't able to get a low speed clock. That's because the Arduino 16 megahertz clock is too fast to get a suitable clock for the low speed. So I faced this problem and I thought that it could not be done. Actually, Michel in his video, if you check on this video, in his peak he selected a very particular clock frequency, which was clock frequency able to give with internal dividers 12.5 and 100 kilobits per second. I was thinking if it was possible to do also with 16 megahertz. At the very beginning I thought it was not possible, it was impossible, but then I was looking inside the Arduino microcontroller datasheet, which is this for the Arduino Uno and the Arduino Nano is this Mega 238, and I found something very interesting. Here, as you can see, I said again, the standard SPI driver can't be used because of the reasons we figured out already. But I found that the Arduino has the possibility of using the UART ports. So basically I use the transmission one, the TXT, the one which is usually used to communicate with other Arduinos or with a converter doing USB, to use this as an SPI driver. So basically what we do, we use the TXT as the data driver, but and in order to get the clock, we use a particular pin of the Arduino, which is this one, the XCK. So why do we use this? Well, if you read the manual and you read the SPI, basically is SPI over UART, you can see that the clock pulse generation is much more flexible when we use this SPI over UART driver. What I mean is that the clock speed can be much better controlled if we use this SPI driver. And I found that basically with the proper prescaler, I could easily get the proper clock speed for either low speed or high speed. This is the basic schematic of the this is the detail how the 74HC00 is connected. So we have both lines going to then 3 of the 4 NAND gates available in 74HC00, and this once again comes from the Labo de Michel schematic he shows in this video. And then the signals go out towards the Holt ARINC driver. Okay, so here it is, the circuit on the breadboard. We have the Arduino here, the 74HC00 here, and the hold driver here. So I reproduced the circuit I already explained to you. We have the two Arduino lines. The data is here, and clock is here, and this pin here is the split selection, which goes then to the hold here. Then we have the 5 volts, which is here. The Arduino let me show you a bit better. Yeah, the Arduino is powered by 5 volts, which are here. Also, the 74HC00 is powered by the same 5 volts, and the hold is powered by the plus 12 volts and the minus 12 volts, which are here. I also added two oscilloscope probes to check what is the signal. So now I'm going to show you, actually I'm powering up with my bench power supply. So we're going to switch on the plus and minus 12 volt and plus 5 volts, and let's see what happens. So we now go here. Here we go. So I'm going to switch on all the powers here. And as you can see, we have the ARINC signal. I have now the channel 1 enabled, but I can also enable channel 2, which is the B signal. So you see both of them right now, and we can also do some measurements on the signal, but we see clearly that it's already looks very good. So we can go here with the cursor, we can do the manual, and we can measure some of the characteristics of the signal. And I don't know if you can see, maybe I can put this here. We have 150 microseconds at the beginning, and 140 is the B one, the B cursor, yes, this one, and the duration is exactly 10 microsecond. So this is the low speed, which was the most difficult one. We can also check on the rise time, and falling time, it's around 1.72 microsecond, and the half beat time, which if I remember correctly is going to be something like this, it's around 5 microsecond. So I would say that's perfect. That's a perfect low speed ARINC signal. So in order to test the board, I connected the ARINC output signals to this altimeter. I'm going to send a label 203 with SSM equal to 3, which is equal to the altitude, barometric corrected altitude. And this altimeter is going to be powered by 115 volts, which are here. And I set up a kind of animation to show me 500 feet up to 5,000 feet, and then going back. So let's switch the 115 volts, so nothing happens because we have still to power the board. So let's power up the board now. And here you can see that we have the flag, which is now going to be off. We are 500 feet now. 1000, 1500, and we can actually see the live stream transmitted. These are the ARINC stream transmitted. You can clearly see the SSM equal to 3 here, and the label 203 transmitted. And then you have a different combination of the data to get the right altitude. So we can see that this PCB actually works, and it can easily be done at home. Would I do it? Yes, it can be easily interfaced with Microsoft Flight Simulator. And you just need to send the data over UART or Wi-Fi, and you're gonna get the right altitude or whatever data you want to send. What I don't like is that we still use this quite expensive Holt driver. So I'm already working on a new version without the Holt driver, which is gonna be much cheaper. So if you liked the video, please like and subscribe, and see you next time.